Hello, this lesson is on simple harmonic motion for IB physics. The goals of this lesson, well, after this lesson you should be able to define and describe simple harmonic motion, give examples of simple harmonic motion, use equations to determine periods, frequencies, velocities, positions of oscillating objects such as masses on springs or pendulums, for example, and describe what damping is and why it occurs and be able to calculate it using Q factor. All right, so simple harmonic motion, what is it exactly? Well, any object that undergoes simple harmonic motion will oscillate back and forth, up and down, or side to side in a fashion so it's periodic. What types of objects could do this? Well, vibrating ions in a crystal lattice. Imagine if you had an ion. Imagine this little arrow is an ion in a lattice. It's going to vibrate back and forth periodically. Well, that's simple harmonic motion, meaning it's moving back and forth in an oscillating way. Pendulums do this. A pendulum, it goes swinging back and forth. So it always gets back to its original position some period of time later. If you have a mass on a spring or a slinky, perhaps. And in fact, we're going to do some examples with some masses on springs to kind of think about this. So let's do that right now. I'm going to use this simulation here, and we're going to talk about some masses on the spring. So if I put this mass on the spring, let's notice what happens. It's going to stretch the spring out, and then it goes up and down, up and down, up and down, and up and down until it eventually dies out. Now, the reason it dies out is because of friction. If I get rid of friction, and I pull on this mass again, now it's just going to keep oscillating back and forth forever and ever, the same period until eternity. And so that's kind of a neat thing. See if there's sound here. Boing, boing, whatever. In fact, if I wanted to slow it down, I could actually calculate the period of this oscillation. Meaning, like, when does it get back to its starting spot? So let's go like 1/4 time here. Maybe 1/16 time. Let's go really slow. And I'll start the stopwatch at the very top and end at the very top. So the period is going to be the amount of time it takes for this object to get back to its original position. Here's half a period. We could have stopped it there and just multiplied by 2 if we wanted to. And we're going to, boom, about a second, 0.99 seconds, about a second for this oscillating object to do that. Now, I'm going to kind of start over, and we're going to test some different variables here. And we're going to test how masses affect the period, how much stretch and all that stuff. So what we'll do is I'll put this on here, and I'll put the 100 gram on the next one, and then I'll put the 50 gram on the next one. So you notice one thing for sure. This one has a much, much bigger amplitude. But which one's vibrating the fastest? Well, it might be kind of hard to see, so let's slow this down. So it takes, what was it, half a second roughly? Half a second for this one to get up and down, or for the 100 gram one, it takes, here we'll reset it, boom, and it looks like about 0.3 seconds, and 50 gram we could expect probably half of that. About 0.2. Yeah, it's pretty close. And it turns out that there's an equation for the period of a mass on a spring, just like there's an equation for the period of a pendulum. And what does it depend on? Well, it depends on a couple things. It depends on, well, obviously the masses affect it, but also the type of spring affects it too. If we have a really stiff spring, it's going to move differently than a really non-stiff spring. So let's see what happens here. So if I apply a mass onto this spring, let's notice what happens. It stretches it. I'm going to slow this down again. It stretches it quite a bit. In fact, if we turn the friction on now and go to real time. All right, so just with the mass hanging on the spring, it stretches it 25 centimeters or 0.25 meters. Whereas this one only stretches it 10 centimeters for 100 grams. So it's about a centimeter per 10 grams, roughly. So we can figure out what the stretchiness of the spring is with an equation. Here, let's go back to Hooke's law here. So Hooke's law says that the force on a spring is equal to this equation right here, where x is the distance pulled back from the string's equilibrium point. So if I pull the spring really far away from its equilibrium point, that'll be measured x as the distance in meters. Force is measured in newtons, so if I apply more force to that spring and stretch it more, or if I stretch it more, there's going to be more force applied. This negative value represents that, hey, the force is acting in the opposite direction that you stretch it. Meaning that if I go back here, if I stretch this spring right here down, it's pulling force up. And the stretchiness of the spring is that K. It's called the static coefficient. Not coefficient, it's a... No, the term for this is elastic coefficient, meaning how elastic it is, meaning how stretchy this spring is. We also can calculate some different things. We can calculate the potential energy of a spring by 1/2 times that coefficient, elastic coefficient, times the distance squared. This x is the distance stretched or compressed squared. We can calculate the period of a mass in a spring, skipping this one for now. T, the period, meaning like how long does it take to get back to its original position. We saw that before. It's equal to 2 pi times the mass. We said it was had something to do with the mass that we added, divided by that stretchiness of the spring, to the 1/2 power, or basically square root of m over k. The period of a pendulum. Let's say we had a pendulum that was swinging back and forth. If we wanted to find the period of that pendulum, well, it's equal to 2 pi times the length of the string divided by the acceleration of gravity to the 0.5 power. Let's say we wanted to find the position of that object, meaning where is it at every single moment in time. Like, for example, if I were to take this object and oscillate it, bam, and I wanted to know where would it be after, say, 5 seconds, for example. Well, the way I could figure that out is to use this equation, where x0 is the position at time 0, and then sine is just a function sine. Omega is the angular frequency of that. We talked about frequency, like how often something occurs. Well, this would be the angular frequency of that. And t would be that time, would be 5 seconds. So sine of omega times t would give us that position. Likewise, we can find the velocity. How fast is it moving at that point? If you notice that at different moments in time, this thing is moving faster or slower. We can actually plot the kinetic energy and notice how the kinetic energy goes up and down, up and down. Potential energy goes up and down, and the total energy stays the same. But this is kinetic energy goes up and down, and that's because the velocity is changing. So we can adjust for that. So you can figure out the velocity of that using this equation. That's all we have time for this video. We'll continue in the next video. We'll talk about damping. It'll be a quick video. We'll finish up on damping, and we'll kind of review a little bit what we talked about today. Anyway, until next time, this is continued to the next video, so take care. Bye.